Okay, hi everyone. Welcome to Colloquium. So this week we're lucky to have Lucia Martin-Merchan from University of Waterloo, who's going to tell us about how compact holonomy G2 manifolds need not be formal.
Okay, thank you very much for the introduction, and thank you very much for the invitation. I'm really excited to be here today talking about these results. So, as it said in the title, our goal today is to understand the construction of a compact, simply connected manifold with holonomy G2 that is not formal. So formality is a topological property that we will discuss later, and we will also discuss about what does it mean to have holonomy G2. But before doing that, let me motivate why I am interested on that construction. So this will be kind of the first part of the introduction of the talk. So a general idea in geometry is that when you have a compact manifold and you impose some partial differential equations, then you get cohomological or topological constraints in a more general sense. A classical example of this are compact Kaehler manifolds. We know that they satisfy hard-Lefschetz property, and also they admit a Hodge decomposition of their space of forms. Formality is another topological property, and it's somehow related to some PDEs that we will see later. And as I said, I'll later define precisely what formality is, but a property of compact, simply connected manifolds derived from Sullivan's result is that you can calculate the higher homotopy groups from the rational cohomology algebra. And how is that related to the PDEs? Well, there is a paper by Deligne, Griffiths, Morgan, and Sullivan that proves that compact Kaehler manifolds satisfying the DDC lemma are formal. And in particular, compact Kaehler manifolds satisfy that lemma, so they are formal. And then people in special and exceptional holonomy started to wonder if compact manifold with a special and exceptional holonomy are also formal. So let me recall Berger's theorem that gives us the possibilities for the holonomy group of a simply connected compact manifold under certain technical assumptions, namely being not a product or not a symmetric space. Well, the holonomy could be the wall isometric group. This is the generic case, not very interesting. And then we have a special and exceptional holonomy groups. These special holonomy groups are related to complex numbers and quaternions. Those related to complex number occur in even dimension, and they are the unitary group associated to Kaehler manifolds and the special unitary groups associated to Calabi-Yau manifolds. Related to the quaternion, we have SPK and SPK times SP1, and those are holonomy groups of hyper-Kaehler and quaternion Kaehler manifolds. And there are two exceptional holonomy groups related to exceptional Lie groups who are G2 and spin 7. G2 is an holonomy group for manifolds with dimension 7, and spin 7 is an holonomy group for manifolds with dimension 8. I will talk later about G2, as I said, but just for you to have an idea, this is the group of automorphisms of the octonions. And the result I mentioned earlier by Deligne, Griffith, Morgan, and Sullivan really help us understand the question I posed for manifolds having a special holonomy. A direct application of it tells you that Kaehler, Calabi-Yau, and hyper-Kaehler manifolds that are compact are formal, and this is because they satisfy the DDC lemma. Also, about quaternion Kaehler manifolds, there is something that we know, and it's due to a result of Aman and Kapovic, who used this result together with the fact that the twistor space of a manifold that is quaternion Kaehler and also has positive scalar curvature admits a Kaehler metric, and then they use some results from, well, they develop a theory to obtain that the base manifold is also formal. So that's a special holonomy group. What about exceptional holonomy group? Well, also in this paper, these two authors conjectured that exceptional holonomy manifold should be formal. But what happened when people studied that problem? Well, compact manifolds with exceptional holonomy are constructed recently. It wasn't until 1996 when Joyce constructed the first compact examples. And we know that they satisfy certain analytical and topological properties, but these are weaker compared to those of Kaehler manifolds. And it's also known that compact 7-dimensional manifolds with holonomy contained in G2, but strictly contained on that group, are formal. And regarding holonomy G2, there were like several results before I studied that problems that try to analyze the problem in different ways. With a more analytical flavor, there were authors who tried to mimic the DDC lemma and get a proof out of that. So Verbitsky found the so-called Kaehler identities for G2 manifolds and kind of built a setup to study the formality. Then Chan, Kariyanis, and Zhang worked out more carefully those details, but they somehow got that those Kaehler identities for G2 do not imply formality on their own. Later, there were, this wasn't later, but from a topological perspective, there were authors who just tried to play with the topological properties holonomy G2 manifolds satisfy. And in this sense, Cavalcanti found a compact 7-dimensional manifold that is simply connected, satisfying all the known topological properties of G2 manifolds that is non-formal. But we don't know if that manifold really admits a metric with holonomy G2. Also, a more positive result with a topological flavor is that of Crowley and Nostrom, who proved that if you have a compact manifold with holonomy G2 and your second Betti number is small enough, which means strictly smaller than 4, then you are formal. And then other people started trying to test examples. And in this sense, there is a paper of Aman, the same Aman as before, and Taimanov, that they showed that a particular example is formal, and then they claim that in the same way you can work out all Joyce's examples, and they will be formal for kind of the same reasons that they found out in that paper. And later on this summer, I discovered the example I announced before, namely a compact holonomy G2 manifold that is simply connected and not formal. So have said the word formality a lot of times, so let's go into...
For that one, that's not one of the Joyce examples, the one that you found, or it is?
Okay, Joyce didn't write this example up, but he could have, but it's not in his paper. So the notion of formality comes from rational homotopy theory, and a tool that they have there are commutative differential graded algebras. So what is that? Well, and in short, I will say CDGA because it's kind of a long word. But a CDGA is a commutative graded algebra that has a degree 1 differential that satisfies Leibniz rule. Examples of these are the RAM algebra of a manifold, and also its cohomology, because you can just think of the differential to be 0. And the notion of equivalence between CDGAs is built out of quasi-isomorphisms. These are like morphisms of commutative graded differential algebra, so they commute with the differential, and we also ask for the extra condition that they induce an isomorphism between the cohomologies. And what is to be formal? Well, a manifold is going to be formal if we can connect the RAM algebra to the cohomology algebra through a chain of quasi-isomorphism having this zigzag form. This is equivalence relation indeed between CDGAs. And here I'm being a little imprecise. I'm talking about formality over the real numbers, and rational homotopy theory was initially built with rational coefficients, but it's non-trivial, but it turns out that if you are formal over the real numbers, then you are formal over the rational numbers, as we have discussed before.
So what extra properties are the AGA supposed to have?
Sorry, what extra properties?
Yeah, so for example, I'm just thinking that there's a dumb thing you could try to do, just look at the map from cohomology to OIC. Got it. So you know why that doesn't work.
Yeah, I mean, the thing is that it should be like a morphisms of CDGAs, and this, I think, is what makes things complicated. Yeah. And as I said at the beginning, the foundational results from Sullivan implied in particular that if a simply connected compact manifold is formal, then there is an algorithm to calculate rational homotopy groups from the rational cohomology algebra. Okay, let's go into, well, is there any question up to here? No? If not, let's go into Massey products. Massey products are operations with cohomology classes. If you have 3, you call them triple Massey product. If you have more, you call them higher order Massey products. And why are they interested for us today? Well, it's an observation that if you have a formal manifold, then all Massey products have to vanish. So if you find a non-zero Massey product on a manifold, then you know that your manifold is not formal. So you can disprove formality by finding such a Massey product. And that's somehow what I did in the example. So I will define only triple Massey product, as I said, and I want to show how this triple Massey product generalizes the idea of linking. And for that, I'm gonna recall a little bit about intersection theory. So you know that when you have a close-oriented manifold, you have an isomorphism between the real homology and the real cohomology. But when you think about the compact the close-up manifolds that you have on your ambient manifold, then you can think of the dual forms in a more geometric way using tone forms. So if you have L, a close-oriented manifold of dimension k, you can find a class called the tone class, whose degree is the codimension of your manifold, and you can pick a representative with very specific properties. I'm gonna call those representatives tone forms, and I'm gonna denote them with the letter tau. So they have two properties. First, if this is our submanifold, our tone form is going to have support in a tubular neighborhood of our submanifold. And then, when we restrict that class to the fibers of the normal bundle, then it's like a bump form with integral equal to 1. Those, as I said, those properties define this cohomology class. When we have two such submanifolds, L and N, intersecting transversely, you have that the tone class, well, the intersection is a submanifold, and the tone class of the intersection is the product of the tone classes. And a way to think about that is that, okay, if you look at the tone forms, they are supported on the intersection when you do the product, and also the normal bundle of the intersection is the sum of the normal bundles. So to construct a volume form for a product, you can just do the product of your volumes form. So that's the idea here. And also here I don't have a picture, but if you have, let's say that this was L, and you have an oriented submanifold whose boundary is L, let's say this part of the picture, then you can find a form that is a primitive of a tone form of L. And I'm denoting there that form by eta, but this primitive is kind of the tone form, a tone form outside a neighborhood of L, and in the boundary you have to interpolate it to 0 in order to make it, to extend it to the whole manifold. But let's say that out of an epsilon neighborhood of our boundary, this primitive is going to be essentially the tone form. Questions up to here? No? Let's then define the linking number, although I think a lot of you would know about this. But if you have two disjoint oriented homologous manifolds whose dimensions add up to the dimension of the ambient manifold -1, then you can define the linking number. And for doing that, there are several ways of doing that. I'm going to just say two. First of all, since they are null homologous, you can find a submanifold whose boundary is, let's say, the first one, and that also intersects the other one transversely. And you can count the intersections between these two submanifolds, taking into account the orientations like in the picture. And also, the tone form of the intersection is going to be the wedge of the tone forms of C and N. So you can also get this number by integrating this interpolated tone form eta, wedge with tau n, which is the tone form of n. So we have these two different ways of computing that number. And now let's think about triple Massey product. Well, you can see that the linking number is kind of giving you a cohomology class, which is the wedge of eta with tau. But you don't start with cohomology classes because you start with null homologous submanifolds. This time we are going to start with 3 cohomology classes, and we are going to define another cohomology class up to something that we'll see later. So we start with 3 cohomology classes, and we ask for the product of 2 consecutive cohomology classes vanishing. If that happens, then we can define the triple massive product, and I'm going to denote it with those brackets, and I'm going to separate the classes by commas. Anyway, so there is a procedure. The first step is picking representatives of your cohomology classes, so I'm going to call them alpha 1, alpha 2, alpha 3. And then since the product of 2 adjacent ones is exact, I'm going to take primitives. So I'm going to call these primitives beta 1, 2 and beta 2, 3. And then I'm going to define a form. To define that, I pair the first primitive with the last form, so the differential of that is the product alpha 1, alpha 2, alpha 3. And then I do the same. I pair the first one with the second primitive up to a sign that essentially guarantees that the differential of this second term is the product of alpha 1, alpha 2, alpha 3. And then I subtract them, so the differential vanishes. And you could consider the cohomology class, but it turns out that it depends on the representatives that you chose. But the error, or let's say that if you mod out by the ideal span by the first and the last cohomology classes, then this does not depend on the representatives. So we will define the triple massive product as this closed form projected to our quotient space. And we will say that it's not vanishing if it's not 0 there, namely it's not in our ideal. Okay, that was a little bit technical, but we are going to understand this with the example that Massey first provided on his paper, namely the Borromean rings. Okay, I tried to do a picture of the Borromean rings with PowerPoint. I don't know. So the Borromean rings have the following property. 2 of them are not linked, but the 3 of them are. So let's say you remove this one. To unlink these 2, you just have to put this up and then pull it down, let's say. Or also you can, using the linking number I introduced before, see that we have 2 intersections here and here when you consider the disk that bounds this link, but one is positive and the other is negative. These are like 2 ways of thinking. And this picture is going to give us a non-vanishing triple massive product when we consider the right space. So what's the right space? Well, we need to embed this on S3 and remove an open tubular neighborhood of this picture. We do that in order to guarantee that we have a compact manifold. So in order to think about the massive product, we're going to first recall that for manifolds with boundary, there is something similar to Poincaré duality, which is called Lefschetz duality, but it works kind of in a similar way. So it happens that, let's say, the first cohomology group with real coefficients is the second homology groups relative to the boundary. And relative to the boundary means that something is going to be close if its boundary is in the boundary of the total space. And it turns out that this this second relative cohomology group, is spanned by the disks D1, D2, and D3. And we are going to be interested in the triple massive product generated by those Tom classes. So let's think a bit about intersection theory. So, of course, the first and the second disk are disjoint. And then the second and the third are not disjoint. The intersection is this line I23. But what happens if you consider this disk C23? The part that is not in the boundary is this I23. So this is a boundary in the relative homology group. And then what happens when you intersect this C23 with D1? Well, you get this line. And this line is on the first homology group, relative homology group, and this line turns out to be non-zero there. And a way of seeing that it's non-zero is that the boundary points lie in two different components of these Borromean rings. So, okay, this is something we can somehow understand. Let's go into the triple massive product, which is the new concept. Okay, so I have these three cohomology classes. So I'm gonna, which were the Tom forms of the disk. I'm gonna pick representatives, as shown 2 slides ago, with those Tom forms. And I'm gonna denote them by tau j's. I'm gonna now pick primitives. Well, first of all, the fact that that D1 and D2 are disjoint makes the wedge product of those forms vanish, so we can take 0 as a primitive. And then the fact that the intersection of D2 and D3 is the boundary of something makes me be able to pick something, a form like this. Let's say essentially the Tom form of C23, but interpolated in their boundary, to pick a primitive of the product. And then to compute the triple massive product, we had to pair the first form with the second primitive plus or minus the first primitive, which is, in our case is 0, with the last form. So we only have one term. So we have to pair tau1 with eta23 that was dual to this half disk. So the fact that the intersection of D1 with there is a typo here, this should be C23. The fact that the intersection of this disk with that one was a non-zero homology class is going to tell me that the product of those classes is not 0 in cohomology. And this doesn't tell us that the triple massive product doesn't vanish, because we had to mod out by the ideal span by the first and the last cohomology classes. But it turns out that the degree 2 component vanishes, and well, this form has degree 2. So we are safe by saying that the triple massive product does vanish in this example. So questions up to here? No? Okay. Then let me shift a little bit and talk about G2 manifold. Well, first of all, I'm gonna talk a bit about the group G2. So for that, we are gonna consider R7, and we know that if you view R7 as the imaginary parts of the octonions, then using octonionic multiplication, you can build there a cross product. let's say that the cross product of U with V is the imaginary part of U times V when U and V are imaginary. And you have a cross product, then you can define a free form by contraction with the metric. And if you pick coordinates on R7, E1 up to E7, you can see that you have this local formula that won't be relevant for this talk. And the group G2 turns out to lie in SO7, and it's the stabilizer of this free form when you consider the action by pullback of the general linear group of order 7. And a nice thing is that the group SU3 is embedded into G2, and lots of our understanding about G2 comes from SU3 geometry. So let me speak a bit about that. If you think about R7 as a product of R with C3, and there in C3 you consider the standard SU3 structure, that is, you consider the standard symplectic form on C3 and the standard complex volume form there, that I am denoting here by omega and theta. Then you can write the standard G2 form, phi naught, as a wedge of dt with this symplectic form plus the real part of the complex volume form. So if you have a transformation on C3 that is preserving your symplectic structure and the real part of your symplectic structure and your volume form in particular is going to preserve phi naught. So what do we understand by a G2 manifold? Well, we will say that a free form on a 7-dimensional manifold, well, on a Riemannian-oriented 7-dimensional manifold, is a G2 structure if we can write them as the standard G2 structure on R7 in terms of an oriented orthonormal local frame. And such a free form is going to induce a cross product in the same way as before. The free form is going to be the contraction of the cross product with the metric. This is just a topological condition. And the obstruction for admitting a G2 structure is V in spin. And now we will put the PDE. So we say that a G2 structure is torsion-free whenever it's parallel with respect to the Levi-Civita connection. And there is a principle, the holonomy principle, that says that this implies that the holonomy is contained in G2. And in case of compact manifold, the holonomy really equals G2 if and only if the fundamental group is finite. And some nice properties of torsion-free G2 structures are that they are Ricci flat. And if you think about the topology in the compact case, there are like weak generalizations, let's say, of the Hodge decomposition and the hard Lefschetz property. But they are not as powerful as in the Kaehler case. And as I said before, compact manifolds with holonomy G2 are very hard to construct, and there are only 4 methods to build them, and all of them rely on our understanding on hyperkähler manifolds and Calabi-Yau manifolds. So I'll mention them briefly. There are like 2 of them that are based on resolution of singularities. They are those of the first constructions by Joyce and also the resolution method of Joyce and Karigiannis. What Joyce did was starting with a torus T7 with a flat G2 structure and making a finite group act over that manifold. So, and this action had fixed point, so you create an orbifold, and then he resolved the singularities of that orbifold and constructed an holonomy G2 metric on it. And that is kind of the analytic and hard part of the construction. Also, the other one involving a resolution is that of Joyce and Carigliani. So they start with a torsion-free G2 manifold M and an involution preserving this G2 structure and with fixed points and consider the quotient. And under some assumptions on the fixed locus, they are able to construct also a resolution. And these other two are the twisted connected sum by Kovalev and an extension that Corti, Haskin, Nostrom, and Pacini did, which are kind of doing connected sum of two Calabi-Yau's cross S1 in a difficult way, let's say.
The fixed points are zero-dimensional? I mean, finite set of points?
They are three-dimensional manifolds, but I'm gonna go into let's say this construction a little bit closer, because I'm gonna need that for the manifold I constructed. So what happens if you have a torsion-free G2 manifold and an involution, and how can we resolve these singularities? Well, the first thing is that if you have a G2 involution and you have some fixed point, then the fixed locus is a three-dimensional manifold. And of course, on the normal bundle, your involution is going to act by minus the identity. And whenever you have a non-vanishing vector field in your fixed locus, you are going to be able to find an almost complex structure on the normal bundle. And this almost complex structure is doing vector product with the vector you are fixing in your manifold. So how do we resolve the singularities? Well, the resolution happens on the normal bundle. So on our original manifold, as I said, we have a real rank 4 vector bundle, but we are identifying it with C2 thanks to the choice of a non-vanishing vector field. When we add the involution that is in our orbifold X, which is the manifold mod Z2, what we have is a singular bundle with fiber C2 mod Z2. But in algebraic geometry, people know how to resolve this singularity. This is an isolated singularity if you only look at the fiber. At the fiber, what we have is an isolated singularity at 0. So you can really blow it up. And what you do is to construct a new fiber bundle, but you replace the singular fiber with its resolution. So we are really changing the fixed locus with a CP1 fiber bundle over this fixed locus. And here I denoted it by Q, and I'm gonna call this like the exceptional divisor. And this glues well when you go back to your manifold, because outside of the exceptional divisor, your resolution is a diffeomorphism. So, okay, yeah, this is what I've already said, that the exceptional divisor is a CP1 bundle over your fixed locus. And okay, this is the resolution, but this is how you construct it topologically. But the hard work again of this theorem is to really build a G2 structure and make it torsion-free. I'm not going to go into any of the details of that, but just, yeah.
It's sort of odd to refer to this as a divisor, since you're not in complex geometry, but it's something of real cohomology too.
Yeah. thank you. It's real codimension 2, yeah.
It was real codimension 4, and then you replaced every point on this fixed locus by CD1.
Yeah, that's it. Thank you. Thanks for the observation. So, okay, so what makes us able to put a G2 structure on this on this fiber bundle that we have just introduced is the fact that the fiber, the blow up, admits a hyperkähler metric, that is a metric with holonomy SU2. But we know that SU3 is contained in G2, so SU2 is also going to be contained on G2. So this embedding gives us a way to put a G2 structure on that bundle. And
so you're using the Gucci-Hansen metric as well?
yes, the Gucci-Hansen metric, yeah. Sorry for hiding the name. And then, as I said, we had a rank 4 real bundle, and we identified it with C2 using a non-vanishing vector field. What this construction indeed needs is a nowhere vanishing harmonic one form for technical reasons. So that's all for the resolution of singularities. Let's look at the example I constructed. So this is
harmonic form is only on the 3 manifold?
On the 3 manifold, yeah. Otherwise, yeah, because we want the space to be simply connected, so you cannot ask for global things. Thank you. Yeah, it's not written. So let's say, big picture of the construction is the following. We start with a torus T7, and we quotient it by a finite subgroup of G2. So what we get is a flat G2 orbifold, and it has singularities, and these are gonna be like 10 connected components, and these are double covered by a torus T3. And using the method of resolution as said before, we are gonna be able to perform a resolution. So at this point, both the orbifold and the singular locus are going to be formal space. But it will turn out that the resolution is not formal. And what makes it non-formal is the fact that when we resolved the exceptional divisor, which are codimension 2 manifolds, are going to give us, via the Tom classes, degree 2 cohomology classes. And it is the product structure of them together with the configuration of the singular locus, what is going to produce a non-vanishing triple massive product there on the resolution. So let's think about that orbifold. So we consider a circle of length 4, and we cross it with the standard torus T6. On the standard torus T6, we have like the standard SU3 structure mentioned earlier. So we can use this SU3 structure to construct a G2 structure on the product via the same formula I said before, namely the G2 structure is going to be the wedge of the angular form on the circle plus the symplectic form plus the real part of the volume form. And then we are going to build the action of the dihedral group D4 cross Z mod 2 square. And then this action is going to preserve the G2 structure, and we are going to mod out by the action, and we will define X as the orbit space. So I'm going to describe the generators of that action. Some of the generators will act freely, and there will be just one generator that will act in a non-free way, and this is the generator that will produce the singularities of our orbifold. what is the action of the group C2? Well, the action of the group C2 square is gonna act on each of the slices of the level sets of our manifold. And on the torus components, it's gonna swap the sign of the first two, and on the third one, it's gonna be a translation, either a horizontal translation by a half or a vertical translation by I/2. So due to the translation, the action of these two generators is free. You can see that the differential of this map lies in SU3. This is like a holomorphic map, and it also preserves the volume form. Next, the generator,
If you compose those two maps, it looks like you've just done you've interchanged Z1 and Z2.
if I compose these two maps, then C1,
same,
and then you do another translation on C3. It's gonna be like a half, yeah, on one, you go like this, sorry. And if you compose them, then you will stay the same in the first two, and you will do a diagonal translation. Okay, the generator of D4 with order 4 is gonna be given by this map. So this map is gonna translate by 1 the coordinate on the circle. Recall that it had length 4, so we are all right. And then on the torus T6, it's gonna be multiplication by I in the first two components. And then on the last component, we are gonna swap the sign of the last one.
What is so the periodicity in T is 1?
Yes, so if you consider its fourth power, then it will translate it by 4. So you had a circle of length 4, so you go here.
Oh, it's a circle of length 4.
Yes. I didn't remark that enough, maybe. So, and here you can see that the order of the map in the torus has also order 4, and okay, the action of that guy is free because it has a translation. This map on the torus has complex determinant 1 and is holomorphic, so it's in SU3 and it preserves the G2 structure. So in particular, we can the action given by these three generators on the torus is free because you are always going to have a translation in one of the coordinates, and we are entitled to define M as the quotient of T7 by the action I have just defined. This is just to introduce a little bit of notation. But I need to mention what is the reflection in the group D4. And the reflection in the group D4 is gonna, let's say, bend this cylinder. So on the T coordinate, on the coordinate of the circle, T goes to 1 minus T, and in the torus, you are gonna have a conjugation. And this action is not free because a half zero is a fixed point for that action, for instance, but it has more. Another thing to note is that on this M, we really need to think about points with which lie in the circle and whose components goes from 0 to 1, just because F is gonna map this cylinder into the next one from 1 to 2, and then again from 2 to 3, and so on. So we need only to pay attention to this part here of our original manifold. So let's think about the singular locus. Well, it's the projection of the fixed locus on our manifold M, and it's contained, since we are bending the cylinder, it's contained in T equals 0 and T equals a half. Here, I'm I am doing a picture of M, which is this intermediate manifold, which is the equation of T7 by these three maps. So it's not singular. And in the fiber, we have T6 mod Z2 squared. And as I said, there are 10 connected components, which are double covered by a torus T3. And they are all calibrated and oriented by the 3-form phi. And as I said, the configuration of the singular locus is important. So I'm going to tell you a bit more about that. So first, there are only 2 connected components at the level set t equals 0. And I am denoting them by A and B. And it happens that if you consider them just on the quotient of T6 by Z mod 2 squared, they are not homologous there. But if you really think, if you allow yourself to do a cobordism using the component in the circle, then you can find a horizontal cobordism. That is, you put V, instead of the level set t equals 0, you go to t equals 1, and then you can just find a cylinder connecting them. Maybe that's a bit, if you don't, like, it's hard to understand if you don't see the explicit computations, but the idea is only that. And then at t equals a half, we have 8 connected components. And they are divided into 2 groups of 4. The special thing is that 2 of the connected components in the same group are homologous on the fiber. And if you pick 2 components on different group that I am calling there by C and D, then we have the same picture than at the level set t equals 0. We can find a horizontal cobordism between them. And sorry, how much time do I have? 5 minutes?
Started a little late, so maybe 5 more.
Okay. So now we had the manifold. So using the method I told before, we can build a resolution. And it turns out that the resolution is simply connected, has holonomy G2, and you can calculate explicitly the second and third Betti number, and they are 11 and 16. And here I'm going to introduce a little bit of notation. I said that we had 10 different components in the fixed locus. I'm going to call them N1, N2, up to N10. And I had just introduced the names of A, B, C, and D. Those submanifolds are going to be among them. And I am going to denote the components of the sectional divisor by EJ. And I said before that these were CP1 bundles over the fixed locus, but it turns out that in this case they are trivial. And you can compute the cohomology groups of the resolution in terms of the cohomology groups of the orbifold and the singular locus. There is a shift on degree because you have to tensor the cohomology groups of the fixed locus with an element on degree 2. And as I said before, the meaning of that element with degree 2 is the Tom class of a connected component of the exceptional divisor. And as I said before, the product rules for them is important. So if we have 2 different Tom classes corresponding to different connected components, their product is going to vanish because they are disjoint, as in the examples of the disks. And what happens with the square of one of those classes? Well, you can compute that the square of, let's say, xj is going to lie in the cohomology algebra of the orbifold. And it's going to be equal to -2, the Tom class of the singular component. And it's a consequence of the fact that the self-intersection of 2 CP1 inside the blow-up equals to -2. And you recall that we had A and B and our manifold, and they were cobordant. If they are cobordant, they are going to have the same Tom class. So the square of the 2 form introduced by the singular component A is going to be equal to the square of the degree 2 form introduced by B. And the same with C and D. And in the last minute, I'll say that the triple massive product, that it doesn't vanish on our manifold, consists of 3 cohomology classes, that of XA plus XB, XC plus XD, and their difference. And I'll say why it doesn't vanish very, very quickly. So you can see that it does not vanish. Sorry, if you prove that the null homologous cycles C minus D and A minus B have non-zero linking number, then you will get that this triple massive product does not vanish. And you can do the computation using the cobordisms we've mentioned earlier, but can I explain it in one? Maybe not. For the questions?
Just go ahead.
Okay. So we had those cobordisms that I'm calling S and T between A and B and C and D. And they intersect in all level sets. So if I instead think about the linking number that I mentioned earlier, if I think just of the linking number of C minus D and A minus one of the level sets here, that I am denoting by SR, you can see the following phenomenon. You can see that if you compute the linking number of, I start with A, if you stop here, then your linking number is going to be equal 0. Then if you stop at t equals a half.
That's not to scratch the screen, right?
Oh,
Permanent.
Sorry, yes. Sorry. The linking number is not defined because the manifolds are not disjoint. And then when you go out of that level set, then the linking number jumps to -2. And that's the reason why it doesn't vanish. So I'll stop here, and sorry for having done it in more time than I should. So. Yeah.
Yeah, so this example is very similar to Joyce's examples where you have a quotient of a torus.
Yes.
The same kind of singular sets, but it's not literally on his list. Do you think that this assertion by, I think it was Cavalcanti, who claimed that for all of Joyce's list that they're all formal?
So the thing is
correct or not?
Yeah, more or less. So the thing is that Ayman and Aymanov claimed that, but the thing is that they were looking at Joyce's examples where the cobordisms between two connected components of the singular locus wouldn't intersect the other components of the singular locus. So they didn't have this phenomenon. But it's a matter of the fact that Joyce maybe didn't construct an example like that, and then they wouldn't have the chance to look at that phenomenon happening.
So it's just a matter of, I guess it's a feature that you have this, is there a dihedral group involved?
Sorry.
The group that's acting on the torus is
The dihedral group cross.
the dihedral group.
Yeah.
He doesn't actually use that, he just uses sums of.
He uses if you only use the dihedral group D4, you won't see it. And it turns out that actually Joyce considered something like that. You cannot actually see it using this group. You need a square here. Yeah.
Another question. How easy is it to generalize this construction? Like, we need to come up with another example. How long would it take?
Oh, wow. I don't really know. Yeah, I mean, you need to observe like what happens with your singular locus when you consider actions of a group on the torus, but it's kind of special. I mean, Joyce constructed a lot of examples and this phenomenon doesn't seem to be there. So I don't know how much it would take. I don't even know, because you could also consider other torus formed by other lattices, but this torus is kind of special in the sense that it admits a lot of symmetries. So if you go to another torus, maybe you don't see that, but I'm just guessing. I actually didn't put more thought on constructing more examples. Thanks for the question.
So I'm a bit confused by what these cobordisms are. So how should we picture sort of B at t equals 0 and t equals 1, their positions being different?
Yeah.
Translation?
Yeah, I'm gonna give you like maybe the particular coordinates and you'll see. So I'm gonna, oops, this is not so efficient. Here maybe. So at t equals a half, let's say, one of the connected components of the singular locus is something like this. If you have something that it is real, then it's fixed by the conjugation. This comes from the fixed locus of kappa, but on T7, not on M. But if you consider the composition of kappa with one of the iotas, I don't remember which one of them, what you are seeing, since in these two components you are composing with a change of sign, now what is fixed under minus the conjugate is the vertical line. So you have something like y1, y2, x3, and maybe here you have to put a quarter or something like that. Anyway, so if you see them on the level set t equals a half, in one component you have a horizontal circle, and in the other one you have a vertical circle, so there is no way they are cobordant. But if you see them, you go with F. Oh, sorry, this is I all the time. I. So these are imaginary circles, as I was saying. So if you multiply by I the first two components and you translate by one coordinate on the circle, then you have 3 halves minus y1 minus y2, and then minus x3 plus 1/4. So so now this is, first it was imaginary, but now it's real. So if you just go horizontally and then you do a little bit of an adjustment in your third variable, then you are going to get a horizontal cobordism. Yeah.
See, I didn't see that F had this I on the Z1, Z2 part.
Yeah, no, it's very subtle. Yeah, like it took me a while to understand it.
Any other questions?
Maybe just, so is the next stage, do you think you can, I mean, it was some kind of conjecture about formality that you disproved, is that?
Yes.
Okay. So is there anything left to discuss about formality? Like, would you try to characterize the formal ones, or is there any hope of that, or is that?
I don't really know. Another step maybe might be I think it's disproving that holonomy, the next spin 7 manifolds, are not formal. This gives, if you think about S1 cross M tilde, then this has holonomy G2 inside the spin 7. So there are manifolds with holonomy contained in a spin 7 that are not formal, but this doesn't have finite fundamental group. So maybe next step is disproving, although maybe it doesn't. This is an step. Yeah, this is a next step. And about that, I don't really have a sense about how to tackle that characterization.
You know that the Kaehler ones are formal.
Yes.
That's not all formal ones
Right.
are Kaehler, but is there something like that for G2 manifold? Can you impose some extra structure and do get formality?
So the only thing that I know, if you require second Betty number small enough, then you have it. But no, this isn't. I don't know. I got this result like in August. So
Okay.
sorry.
Question.
So the spirit of this construction is very much like Joyce's original paper, but it actually, his list of examples is not that long. Whereas there's this construction that Kovalev tried it, actually Kovalev's paper has a mistake in it. But anyway, Haskins and so forth fixed it. And they get like tens of thousands of examples out of this. You have any sense of whether these kinds of twisted connect sums,
Okay.
some of them are non-formal? Or?
So I don't know. One thing is that when you do a twisted connected sum, normally you get second Betty number very small. So with the first choices you have, then maybe it's smaller than 4, and then they are formal. And I've not seen like any paper discussing that. And I don't know, I'm not that comfortable with this construction to have really an intuition on if they are going to be formal or not. Some people thought there could be something there. I know that, but I'm not comfortable with saying anything more about that. Sorry.
Did you say your example is B211?
Yes.
So it's unknown between 4 and 11?
Yeah, that would be another idea. Yeah, getting like the B2, thinking about, because this paper tells you if something is bigger than 4, then you have to be smaller than 4, then you have to be formal. Is that bound accurate? This is another question. You can think about that.
Is there a purely, I don't know how you arrived at this specific choice of, very clever choice of finite group, but is there some intrinsic reason looking at the Lie group G2 to choose this? You don't want something that's just contained in SU3, right? That probably can't work.
Yeah, if you get something in SU3, then you don't kill the fundamental group, so you need a reflection, something that is outside SU3. This kappa plays that role. That answers the question of killing stuff in the fundamental group. It doesn't answer the question about really getting on formality. No, I don't know if that's related to the subgroup somehow.
I think simply connected manifolds, all simply connected closed manifolds up to dimensions, including 6, are formal.
Yes.
Right? So the first dimension you can have a non-formal manifold is 7.
7.
So you might say the best metric possible on a non-formal manifold is G2.
Yeah. Yeah. Yeah, that's a good observation. Thanks. I will advertise that. Yeah. And I will quote you maybe.